Right, everybody, I think we can start. Welcome back. I don't know if this is normal, it looks different. No. All right. So let's pick up where we left last week. So where we are at. Okay. I think that was the last slide that I showed you last week. So we are talking here about the radial wave functions in the Schrodinger model. So remember that the radial wave function depends on n and l, and those are the functions for each value of n and l. Okay. Very good. So what I would like to start talking today is about radial probability. Okay, so radial probability is basically the probability in finding the electron as a function of the distance from the nucleus. All right. When we work with the probability, the first thing we need to do is to multiply the radial wave function by itself. Okay, so that is needed to eliminate any negative values. Okay? So that's the first thing. And the second thing we will need to do is to multiply by 4 pi r squared. Okay, so this is necessary because we are looking at probability for a very small volume. Okay. All right, any probability graph will then have on the y-axis probability, and remember that probability is r squared times 4 pi r squared. Okay, so this here is the derivative of the volume of a sphere. And we are going to trace this as a function of r. And r, this is distance from the nucleus. Yes, sir.
What is big R?
Big R is the radial wave function.
Oh, okay.
Okay, so those that I showed you.
Yeah.
You got it? And the small r, that's the distance between the electron and the nucleus.
Okay, so the big R is the probability.
Yeah, exactly. Exactly. Okay, each orbital will have a different graph of probability. So let's start here with the simplest one, 1s. If we graph the probability as a function of the radius, we are going to see something Like, okay, first important point in this graph is this one right here. If the distance is 0, that means we are right at the nucleus, right? The probability to find the electron at the nucleus is 0. So for any wave function, the probability to find the electron at the nucleus is 0, always. Okay? If we move too far away from the nucleus, what's going to happen with the probability to find the electron?
Also, this is 0.
Exactly, because that's too far, right? So it's unlikely. So if you move too far, the probability also vanishes to 0. Those 2 points or 2 observations will be valid for any orbital that we are working with. And finally here, we have this point here. And this is the max probability. Does the max probability mean that the electron is there? No, but it's very likely to be there. Okay? So if you had one chance, you would go here. And it's more likely to be there. All right. Any questions?
Can you go back to what big R is again?
No problem. The DR,
Yeah. I was looking back in my notes, and it's R sub N, right?
it's the same thing.
Okay.
Yes, yes. Those are the radial wave functions for each orbital.
Okay.
Okay. And this here, that's what we are going to graph. And again here, I don't need you to memorize any function, but you have to understand what's the logic and how each function works, right? That's what we will do here. Okay, this is very good. So the 1s orbital is the simplest one. And now let's get orbitals that are a little bit more complex. Again, here, we have probability on the y-axis as a function of the distance. So the green line here shows the 1s orbital. See here that the probability is pretty close to the nucleus. And then when you start to move to the 2s and 3s orbital, this max probability starts to shift far away from the nucleus. First question for you is, does that make chemical or physical sense? The probability moving far away from the nucleus? Yes, because you are moving to a more external shell, right? Very good. And see here, for all the graphs, we have probability 0 at the nucleus. And as you move far away from the nucleus, starts to also vanish to 0. Yes.
What are atomic units? That it's in our
Don't worry about it. Okay. So atomic units are based in the Bohr radius. It doesn't matter. What matters is that the x-axis is related to this. Yes.
So the max of each peak gets lower because the probability of the electron being there gets lower as because it stays farther away from the nucleus.
Yes, because you get too scattered because the orbital is too large. So now you have probabilities across a larger volume, and that's why you see a decrease in the max probability. Okay?
Why do you see them go up in humps and then come back up? And
That's my next point. Yes. So now I want you to focus on the 2s orbital, and then we will move on to the 3s orbital. For the 2s orbital, can you see here that you have one little hump? It touches the x-axis, and then you have a large one, right? The point where it is, touching here, it is between 0 and the infinity. So this point where you have 0 probability, this point right here, this is called a radial node. Okay, so radial nodes are additional points where the probability is 0, and those points are always in between 0 and the infinity. For the 3s orbital, according to the graph, how many radial nodes do you see there? 2, right? So you have one right here that coincides with the 2s, and an extra one right here.
Right at close to 0, obviously it's in the nucleus, can't be there. But isn't there like a tiny bit that has to be away from it, like never get to 0, but like how close?
How close it gets?
Like I mean, this is beyond this class, but if you magnify that, would it get weird?
I mean, I cannot magnify here
Yeah.
because it's the resolution from the book, right?
Yeah, of course, but I mean, like conceptually or theoretically, would it get strange as it gets really close to the nucleus?
I think because these functions, they are usually exponential, it decreases really fast when you decrease the distance. Okay? So it's a very, very fast change, almost like a chop,
Right.
but not a chop.
Yeah. Yeah.
Okay?
And we would see it go right to 0.
It has to.
Yeah.
It has to.
Yeah.
Yes. It cannot be anything different from 0. Okay? And again, remember that you are multiplying the function by r squared. And that's what causes to go to 0. If r is 0, it's a multiplication, you vanish everything. That's why. Okay. Okay, so now let's talk a little bit about radial nodes. So there is actually a formula to calculate the number of radial nodes. It's a very simple formula. We're going to do m minus L minus 1. And this here will give you the number of radial nodes. So therefore, when we have the 2s orbital, n is equals to 2, L is 0 because we are talking about the s orbital. So therefore, we have q minus 0 minus 1. That yields 1 radian.
Can you repeat those? Well, I can't really see the equation.
It's going to be n minus l minus u. Mhm. Yes.
The Jay was wondering if it's possible for you to share the screen.
I guess I was sharing, but let's see here.
The first day. My last
No.
person class couldn't even get it working at all.
Oh, then I feel good. Then I feel excellent.
Yeah.
Okay, ask her if now she can see it.
I think her internet went out because she's not up there,
Oh,
but
so she should be. Well, hopefully they were seeing it. And I feel bad, but not much I can do, I guess.
One of my other inspectors was able to pan the camera. So it stops following you.
Oh, and just follow this, just get stop here. I know that there are some presets here.
Which one's the playlist?
I don't wanna press anything here,
Right.
and then,
Then it comes out.
yeah.
I mean, the notes are online if they really want to look at the notes. They're online.
Yeah, I've been just doing it on Canvas.
Hey, Danny, can you see the slides now or just you see?
I can see the slides, but it's in your form, so it's not actually in slides. It shows like notes,
Oh.
your slide, and the next slide.
Let me-
I mean, I don't know about the rest of everyone on here, but I'd rather look at the slides on my own and be able to see what you're writing on the board more.
Oh.
Yeah.
Yeah, I think because it makes you really small if you have the projection up, so we can't really see the board.
Oh, I see.
So I think it's easier for us to look at it.
That's the document.
Yeah, just to look at the document and then watch you write on the board.
So you still cannot see the slideshow, right?
We can see the slideshow now,
Okay, okay. Oops,
not anymore.
hold on. What about now?
Yes.
Let's do this for now. It's so complicated. Yeah, just a little bit more. Okay, so radial nodes are going to be points in between 0 and infinity, where probability is 0. And what is observed is that higher number of radial nodes decrease the stability. Okay, so higher the number of radial nodes, lower is the stability of the orbital. Okay, so if you look at the probability graph of 1s, 2s, and 3s, can you see here that there is a small probability that the 1s, 2s, and 3s electrons are kind of in the same place? So that means at the same time and in the same area, you can have a 1s, 2s, and 3s electrons.
You talking about where they overlap
Yes.
together in that small
In
area?
that small area right here.
Oh, I thought you were talking about next to it.
This one, yes, this one also,
Okay,
but here you have larger probability.
okay.
Okay. Have you ever heard about tunneling? So if you have one electron in one s orbital, it can tunnel to a 2s orbital or a 3s orbital. And here is the reason for that. Because you have a region that you have the same probability to find all of them. Okay? So it's like they catch a tunnel and move to another orbital.
Is that just the case for the s orbitals or?
If you put all together, you are going to see that a lot of areas they can overlap. Okay. So that sounds weird because the models that we have in our head, everything is static and physically kind of divided. But imagine the thing as one nucleus in a cloud of electrons. Okay, and they can be anywhere. And here we know kind of where they should be. Doesn't mean the word there. Right? Okay, very good. Okay, we talked a lot about the radial part of the Schrödinger equation, which is very complex. Now let's talk about the second part of the equation. I'm showing here in light blue, and that's going to be the angular wave function.
Is that a cross or a multiply?
That's a multiplication. Okay, for the angular wave functions, y, l, and l, they are dependent on two quantum numbers. L, angular momentum quantum number, and ML, magnetic quantum number. And again, there are only a set of possible numbers for L and L that will solve the wave function. Okay? Only specific numbers for L and L will be allowed. The angular momentum quantum number, L, is related to the electron spatial distribution and is a function of n. As we saw, L must assume only integer numbers starting from 0 and going all the way to n minus 1. Okay, so L is the subshell. For the magnetic quantum number ML, it is related to the orientation of the magnetic momentum of the electron in the space. And it is a function of L. ML must assume only integer numbers starting from minus L and going all the way to plus L in 1 unit increments. Okay, so what we said there, for each value of L, we will have allowed values of an L. We always start from minus L, 0, go all the way to 0, and then plus L. For example, if L is 1, if we have L equals to 1, the lowest value possible of ML is minus L, minus 1, and the highest one is plus L, plus 1. And then we are going to fill the gap, moving in 1 unit increments. Minus 1, next one is 0. And after 0, we got to plus 1. Okay? So therefore, for L equals to 1, 3 values of ML are possible. Minus 1, 0, and plus 1. Okay, so I'm not going to fill up the table, but you can do it later. For each subshell, so figure out all the MLs that are possible. For L1, we have the D subshell, it's already there. We can practice for S, D, and F subshells. All right. So if we want to take a look in the formula of each angular wave function, so that's what you are going to find. So here we are using polar coordinates, and here we are using Cartesian coordinates. Okay. All right, so does that ring a bell? Okay, so S, see here, the function does not depend on X, Y, Z. So any direction you go is the same, and that's why it is a sphere. For PZ, it depends on the Z direction, PX, X direction, PY, Y direction, and so on and so on. So the draw of the orbital comes from the angular wave function. And what we see in the draw is the region that you have highest probability to find the electron.
George, and first 2D on the Cartesian, got an R in there on the bottom.
This here,
Got an R?
yes, that's the same R as this one.
So it's just a square root of x squared plus. Y squared.
Essentially, yes, yes, yes. Mhm. And so one interesting thing here. So what happens here if z is 0 for the p0? What will happen with this function here? Exactly. So you have a region where the probability is 0, basically, right? And you can play with all the orbitals and find how many points or where are the points where the probability is 0. And let's see. Yes, that's the next thing that we'll talk about. Okay. So when we have a draw of the orbital and we identify points where the probability is 0, we have what's called angular nodes or nodal planes. Okay, at this point, I want to make sure that you understand the difference between the radial node and the angular node. For the radial node, we are always looking at the graph probability as a function of the radius. For the angular node, we are looking at the picture of the orbital. Okay? So two different things here.
So an angular node is a place, it's an angle where it can't be.
Yes. Exactly. Exactly that. Exactly that. So usually a plane, because we are in the 3D space.
That's an angle. Oh, sorry.
Yes, 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 yes.
Is that represented by that first image on the top of the picture? The, like the cone and then the planes,
Yes.
are those the areas,
That
those
is,
the nodes?
those are the nodes.
Okay.
Yes, yes. So here you have the d orbitals on top there. Right here. And the planes in the light green, those are the nodal planes. Okay. So for the last four, it's very easy and it's less complicated to see the planes here. The dz squared, you don't have a plane, you have like a cone, but it's the same concept. And to determine the number of nodal planes, you are just going to use L. P orbital, L equals to 1, therefore 1 nodal plane. D orbital, L equals to 2, therefore 2 nodal planes. And those are the ones that we see in the picture. Okay, very good. So we covered ML, ML, radial and angular wave functions. So let's talk about the last quantum number. So there is a fourth quantum number used to differentiate two electrons. And this quantum number is the magnetic spin quantum number, MS. And there are only two possibilities, plus 1.5 and minus 1.5. Okay, with that, we covered the four quantum numbers, N, L, ML, and MS. And that's what we have. Okay, so each quantum number will give some sort of information about either the energy or the shape of the orbital or the distance between electron and nucleus. Yes.
How did you figure out how many angular nodes there were with using L?
Number of angular nodes is equals to L,
Okay,
just L,
okay, and then we determined the value of L based on
on,
N.
on the orbital, right? Okay, yes.
So L for S is 0.
Yes.
Right.
So S orbital does not have any angular nodes. Okay,
Use 1.
this one, so one angular node.
So that's that flat plane in between the two
Yes, the two,
hourglass.
I forgot to read my model, yes, but yes, you have the two lobes. Right at the zero, you have a zero probability right there. And that's the angular node. Nodal plane, that's the node that is. Okay, so biggest confusion here when we talk about spin, people think about electron spinning. If you have something that doesn't have mass, you cannot spin, right? So spin quantum number is just a number that's needed to solve the Schrodinger equation. So any electron cannot have the same set of quantum numbers. So we need the MS to differentiate two electrons that are in the same orbital. Okay, so that brings us to electron configuration. You probably remember about that. We need to go over in a lot of details. So we can have a max of 7 shells. Each shell will have different orbitals, and each orbital will have different values of an L. Okay? Each slot can handle 2 electrons. You must have one up, the second one needs to come down. They cannot have the same spin because that means the same set of quantum numbers.
So is that the magnetic spin quantum number, just the arrow pointing up and the arrow pointing down?
Yes,
Yeah.
yes,
Okay.
yes, yes. Okay, so I believe you remember how to do the electron configuration, so I think we don't need to do the diagram, right? I want to talk about one thing related to the nitrogen. Nitrogen Z equals to 7 belongs to the group 15. So therefore, we have 5 valence electrons. So let's look at the valence electrons for now. So what we are going to have is 2 electrons in the 2s orbital, one up, one down, and then 3 electrons in the p subshell. So what you have learned is that you go one, the next one goes here, and the third one goes in the last slot. Why you don't have two in the same slot and one by itself?
Maybe it works bigger now.
Why? Repulsion, yes. And see that all of them are pointing up. So technically they are the same, so they can interchange slots. Because you are in the same orbital, again, it's a probability. So at one point, nothing blocks this electron to come here and this one to move over there. And this exchange creates stability. And that's why you go slot by slot and not pair and then move. Okay? It's always a matter of energy and achieving stability. Any system, most of the systems in nature will do that. Could you have paired up and another slot and nothing in the other slot? Attention, can you have? Nothing is forbidden, right? Is it probable? Is less probable. Okay, so it would be a higher energy state if you have that.
Isn't that what NMR is based on?
Kind of spectroscopy is basically that, right? You are exciting electrons, destabilizing the system, and then you do it. Okay, and then let's do here, go back in our memory. Remember the Hunt rule. Electrons must be placed in the orbitals to give the maximum total spin possible, because that will allow them to exchange, stabilizing the system. And Pauli exclusion principle, each electron must have a unique set of quantum numbers. You cannot have the same 4 quantum numbers for 2 different electrons. One of them must be different. Okay, so for example, the 2 electrons in the 2s orbital, they have the same M, same L, same ML, but different MS. And that's enough. Okay, so this course is basically a CHEm refined. So you must remember what's there, and then you can go a little deeper. Okay, so now quick questions for you, and then I think that will be the end. So try to figure out if this sequence of quantum numbers are possible, and also this sequence here at the bottom. Okay, so the question is, a electron can have m equals to 2, L equals to 2, and L equals to 0. That's the question. And basically the same thing at the bottom, but n equals to 2. Jerk, what's up? What do you think?
No for the first one?
No for the first and the second?
Yeah.
Let's see. All right, so remember here, each shell is composed by subshells, and that's L. Number of subshells is going to be lower limit. We have here n minus 1 all the way to, sorry, 0, right? Starting from 0 all the way to n minus 1. Each shell, it will subdivide again in orthos, and that's ML. Lower limit for ML minus L. 0 all the way to plus L. And finally, ML will split again into, which is NS plus 1.5 minus 1.5. So if we have the second shell, n equals to 2, can we have L equals to 2 for that shell? Because the max is exactly. So because of that, this set of quantum numbers is impossible. 50%, huh? 50% right so far. N equals to 3, L equals to 2 is a possible value. For L equals to 2, there is nothing that say we cannot have an L equals to 0. Okay, so therefore, the second set, it is possible. Questions? Oh, one thing. When you guys are doing homework or in class assignments, do not worry in writing the question. Okay? Don't lose time doing that. I already know that. Just give me the answers. You either can show your thinking or just put the final answer. So it's up to you. Yes, just.
For that, like the homework setting classes, are we turning it in person? Or should
If you are in person and you want to just drop the paper here, I'm more than happy to do that.
Okay, but it's gonna be the same situation on Friday as it was last Friday, right?
I
Okay,
guess.
okay,
Okay, so this Friday we do not have, right?
right, so the
The
next.
next
class.
one, yes. If you wanna come, I have to be here.
Right.
So you can give me the paper or submit to campus.
So on that topic, so you said we could like converse with other people.
Yeah, so if you guys are here, you can discuss whatever you want. So that's, if nobody knows anything, doesn't matter to discuss, right?
Yeah, exactly.
This is not that going to make or break whatever you learn. Okay, so if there are no more questions, then we can finish at this point today.
When you're talking about the jumping within the orbitals, that's Spen's rule? That's the name of the rule you were speaking of?
Yes,
Okay.
yes,
Okay.
yes. Yes.
Yeah.